Welcome back. This is Mr. Dahlstrom. Continuing on with the energy notes. Our last video was about elastic potential energy, spring constant, and a little bit about Hooke's law. That wrapped up the introductions of the types of energies or work that we're going to be introducing into this unit. There are other types of energy, electrical energy, chemical energy, that we'll talk about a little bit later. Today's lesson, I wanted to talk about conservation of energy, and in that term, energy transformation. So breaking down that word trans means change, formation, changes the form that it's in. So if we look at conservation energy, it relates this idea that we can change the type. So conservation energy states that energy can never be created or destroyed. It can only be transformed from one form to another. The scenario or the analogy here is that if you have a $20 bill and you give it to somebody else, they can break that down into other forms of currency, but all of it will add up to $20. Now, I didn't destroy $20. I just have $20 less. It's not like I took $20 and I destroyed it. It just went into other forms there. Similar idea with energy here. So these are the energies that we have, just kind of a little checklist to know whether or not a scenario is going to have one of these energies transforming to one of them, or multiple to multiple, or whatever. So the equations all next to each other. So whether or not we're going to have kinetic energy, if it states that it's moving, then we're going to have kinetic energy. If it states that the object is at a height greater than 0, then we'll have gravitational potential energy. Much like the roller coaster game that we played. If it has basically another way of thinking about this one, if it has a spring, we can ask ourselves, is there a spring? Not only is there a spring, but is it compressed? And the reason why I have an absolute value there is it stretched, or is it compressed, or whatever direction? Is there a spring? Is it being stretched or compressed? If that answer is yes, then we have elastic potential energy. And then the last one here is work. We talked about work as how you can put energy into a system. For example, with that roller coaster game, there was a motor, there was an engine, there was something that was doing positive work to put energy into the system to allow the roller coaster to go. How we're going to be thinking about work, at least in terms of these transformations, is that this work is going to be due because of friction. And so the work due by friction is equal to the force of friction times the distance that the friction is acting on the object. So if the coefficient of friction is greater than 0, then we have some amount of friction there. We're going to look at a very introductory level problem here. Take this away and look at an example we had very, very early on in the year when we were doing free fall. And we were looking at how would we solve it using energy, and then how do we solve it using the kinematic equation here. This would have been the fourth equation we had out of our 4 equations. So, dropping a rock, giving some information. So here I have a rock. Sorry, this got cut off there. The initial velocity of the rock is 0. I am dropping. There's a key word. The height is 10 meters. We would have called this delta y was negative 10 meters. The reason why we're using positive here is because we're also telling gravity positive 9.81. The mass of the rock is 5 kilograms. We'll see whether or not we need that. So we're trying to figure out what is the velocity of the rock if it is dropped from 10 meters high. When it hits the ground, how fast is it going? And so the strategy that we're going to look here is we want to look at what's going on at the beginning. So before it is dropped, and then after. And after is representing right when it strikes the ground. The beginning scenario, the end scenario. And you say, well, why are we just looking at the beginning and the end? We did this when we were doing the kinematics as well. When we were trying to figure out, even projectile motion, we were just concerned of how fast was it going in the beginning, how fast was it going in the end, what was the time in the beginning, what was the time in the end. We didn't really care about what was going on during, because we're just we have information about the beginning and information about the end. One strategy of kind of doing this here, there's 2 strategies, is to list out, I guess maybe even the beginning, is to list out all the types of energies that we could possibly have. This is sort of an introductory level just to show you sort of what we're doing. And then we would set them equal to, or at least show what are all the, we'll not set them equal to them yet, kinetic energy plus gravitational potential energy plus elastic potential energy plus work due to friction. We do not have all these necessarily, but we're going to kind of go through the checklist that we had on this page right here. So we'll ask ourselves, is it moving at the beginning? Nope, it's being dropped, so we don't have that. Is it at a height greater than 0? Yes, so we do have gravitational potential energy. Is there a mention of a spring? Nope. And is there any mention of friction? I will be very clear if there's friction. Usually friction will be like in a friction patch. There's no air resistance here, so there's none of that. Now we'll look at the end. When the rock is about to strike the ground, is it moving? Yes, it's moving because we talked about this before. If an object wasn't moving when it struck something, then it wouldn't hurt if it hit you. So yes, it is definitely moving when it strikes the ground. Is it at a height greater than 0? We're not talking about the beginning, we're talking about at the end. We're assuming that when it strikes the ground, there's no height. There's still no mention of a spring and still no mention of friction. Conservation energy says that all the energy in our system has to be conserved. Another way of saying that is that all the energy in the beginning, and in this case, the gravitational potential energy, is equal to the amount of energy we have in the end. The rock is transforming its energy from gravitational potential energy to kinetic, so whatever amount this is over here is going to be transformed into this. And this is a scenario where we just have one energy going to another. There are others where we have multiple energies traveling into different types of energies there. So if we can set those equal to each other, mgh, I'm actually going to, hold on here, I have a paper here. I'm going to use this area we have. Sorry, I have 2 pieces of paper here. Erase that. Gravitational potential energy is mgh. I can set that equal to kinetic energy 1/2 mv squared. In this scenario, not always, in this scenario, mass does not matter. We'll kind of relay that to, if you remember, we did kinematics, there was never mass over here either. So let's see if we can see some similarities between them. Let's think about what we know and what we do not know. Okay, we know gravity. We're using positive 9.81. We know the height. The only thing we do not know is the velocity, and that's what we're trying to find. So I'm gonna rearrange this equation real quick, see if I can solve for v. So I'm gonna multiply here. So I'm gonna get 2gh equals v squared, or if I rearrange it, v equals the square root of 2gh. That's one way I could do it. We'll come back to that. But if I just want to straight plug in the numbers here, over there, g is 9.81, height is 10, equal to 1/2 times our v, or final velocity here, squared. So when we do calculate that out, I believe I already did that before my class, 9.81 times 10 times 2, square root of that number. It is right. Sorry. Times 2. We get approximately about 14.01 meters per second. Okay, so that's how to do it energy-wise. Let's compare this to how we did it here. This is one of the connections that kind of AP Physics really kind of brings forth, is the connection between the different units, where we just solved it using energy, and here we'll see if we can do it the same. If we rearrange it, we get VF is basically VI squared. The initial velocity is there, so that's 0 squared, plus 2gh. Notice that V equals the square root of 2gh is what we're going to get here as well. Maybe it's to show that we can derive some of our kinematic equations from energy, or vice versa. Now we can use 2. When we were doing this, we used negative 9.81 because we also had a negative. We were talking about direction. I'm going to use a positive 9.81 here because that's what we were doing here, and a positive 10. So it doesn't matter whether you use positive 9.81, positive 10, or negative 9.81 times negative 10. You're going to end up getting a positive number inside of here. And when you calculate the velocity here, you get 14.01, which makes sense because you're using basically the same equation as we do over here. So you may be saying, well, why in the world are we learning this method over here if we already have the kinematics? Well, this is just one scenario. The only reason we were able to use this is because we had one specific type of energy going to one specific type of energy here. We're going to look at some more later on, where we're going to have many transformations. So one of the last ones I'll just show you, and it's already been kind of solved just to save some time here, is an example of a pinball. And this is not as a pinball. Pinballs, I made this up in class. Pinball might not be the best scenario here. We'll just say we're using a spring. And in this scenario, we have a ball or some object. This is frictionless. Is compressed. So when it's compressed, it's not moving. We're assuming the height is 0. It has a spring constant. I just made these numbers up, 1,000 newtons per meter. We're compressing it 0.5 meters, negative 0.5 meters, or positive. It doesn't matter in this case because of elastic potential energy does not have a direction. And I just said the mass is 0.1 kilograms. At the end, we are wanting to find what height do we need over here in order for this ball to be going only 5 meters per second at here. So we're going to go and look over here what type of energies we have over here and what type we have over here. Notice we're only looking at the beginning and we're looking at the end. It doesn't matter if there's no friction here. It doesn't matter what type of things, or if there's corkscrews or loops or other hills here. What matters is all the energy at the beginning of the problem has to be the same as all the energies at the end of the problem. So even if we had multiple transformations of energy before and after, what matters is beginning and end. And if you see how I did this work here, and it's already solved out, the type of energy that we have in the beginning is only elastic potential energy. It's not moving, so there's no kinetic. There's no height above zero, so there's no gravitational potential energy. There's no friction. There's no mention of friction here, so there's no work. So all the energy that we have in the beginning for this scenario is all in the form of elastic potential energy. At the end, excuse me, it says that it's moving, so there's definitely going to be kinetic energy. And it doesn't necessarily say that there's a height. The picture shows that, but we're looking to try to find this height, and that height would be in the form of gravitational potential energy. So here we have one energy in the beginning, but here it's turned into two types of energies that have to add up to elastic. So if we write it out like this, what our equations are, and think about what we know the spring constant, we know how much is compressed, we know the mass, we know the velocity at the end, and we know what gravity is. The only thing we don't know is what the height is here, and I wrote it out in a previous session here, so just basically plug in. K is 1,000, X is 0.5, mass 0.1, velocity speed 5, mass 0.1, and gravity. And so we solve for H, and this is what I recommend that you kind of break it down here. A lot of the energy, not a lot of it, all the energy in the beginning is elastic potential energy, and it's 125 joules. That kinetic energy, the fact that the ball is only moving 5 meters per second, because it has such a small mass, it's only 1.25 joules. A huge majority of the energy at the end is going to be in the form of gravitational potential energy. This makes sense here in terms of the coaster game that we played, because if it was going too fast at the end, if it went and crashed through the barrier, the solution was to raise the end up. By raising the end, we increase the gravitational potential energy in order to decrease the kinetic energy. Vice versa, if it got stuck and wasn't going fast enough, we would lower the track, lower the gravitational potential energy, thus increasing the kinetic energy. So when we solve for H here, we get about 126.15 meters. If the height of this was more, then we would have to drop the velocity. If the height was less, we would have to increase the velocity. So that is a kind of a quick example we went through in class of how you would do this, where we're only concerned with what's going on at the very beginning and what's going on at the very end. One thing to also bring is like, well, wait a second, how can it not be moving? If it's not moving at the beginning, how can it get over here? Once again, it's just like the dropped rock. Okay, the dropped rock, the rock wasn't moving at initially, but it is accelerating. The spring is accelerating up there, so that's why we're saying that it's not moving at that point. So I'm going to wrap this lesson up tomorrow, or not tomorrow, later, another time. I'm going to upload this document right here. This is one that I've created, energy transformation problem set. We'll talk about, what is the shape? How does the shape of a track define the velocity? What are some other scenarios here, like a Nerf gun? Can we figure out the mass of the object based on some information here? Here's another example of a spring and a loop-de-loop and trying to figure out how fast. And then we'll try to talk about what if it's going too fast at the end, how much, basically if we have a certain coefficient of friction, let's say we have a friction patch, how far, how long does that friction patch have to be in order for us to come to a complete stop? So we'll look at that at another video. But that will basically be the assignment that we'll have in class. And so we're going to wrap that up. And as you're watching these, you should be watching these, how I probably should have said at the beginning, you should be watching these and taking notes as if you were in class. That's the best way that if you come back, you'll be ready to go. So I'm going to go ahead and sign off, and we'll have another video. Thanks for watching.